Okay, thank you very much for inviting me, and I'll try to talk a little bit about anaerobic digestion. It's going to be quite basic discussion about the digestion, about the role of digestion, and a little bit about the process and measuring how to get good conditions in the anaerobic digestion. So the basic stuff. Anaerobic digestion is about organic pollution, anaerobic microorganisms, and biogas is produced. So these are the basic postulates which apply to the anaerobic process. It produces energy, it produces biogas, and it must be anaerobic. If we go and compare the aerobic and anaerobic, of course, there are two main differences in aerobic and anaerobic process based on the energy value. So based on we can measure energy by COD. And based on energy value on COD, we see that it's in aerobic process, there is energy goes to the heat, mostly to the heat, and some of the energy goes to the sludge. So there are heat losses. We don't see it in the wastewater treatment plant, but we see in the composting, for example, in aerobic composting process, we see the heat which is used for the deionization of the composting, for example, and there is a bigger sludge production. In anaerobic, instead, there is the energy goes to the biogas. So from 100 kilograms of COD equivalent, you get about 300 kilowatt hours of energy used. And the sludge production is not. So the aerobic, lots of sludge, lots of biomass remaining, and anaerobic, less biomass is remaining in the process. To look more in detail into the anaerobic process is a multi-stage process. First, the bigger components in anaerobic or digested bio-waste or biodegradable stuff is degraded to the smaller molecules, fatty acids, lipids to fatty acids, amino acids come from proteins, the carbohydrates, polycarbonates, then you get monosugars, then there's acidogenesis, and so the first part of it is going to be down to the acids, and the acid that hydrogen is forming, and the second part is the metabogenesis. It's after the plastic, everything which goes over the acetate is after the plastic, mainly by arche, going over to form methane, and hydrogen is produced also as byproduct or intermediate product, and it's also hydrogenotrophic microorganisms form methane finally. So it's also there is also gas produces hydrogen in the same type of process. If you look on the pH of those two different areas of anaerobic digestion process, the pH for the first part, so for the acetogenesis and acetogenesis, optimal pH is much lower than the metagenesis. So if we can have those two separated, those two processes separated, then we can of course have much more efficient process, because if we have them all together, then the pH range is optimal for the full consortium of microorganisms is much higher. So we need to maintain the pH of the metagens. And also the same applies to the reduction potential. The normal oxygen reduction potential is quite low in the full process, but in the acidogenesis, it doesn't really matter whether it's aerobic stage or not, or it can vary from +400 to -300, but in metagenesis, it must be below 200, -250, the oxygen reduction potential. So the process can be divided in separate parts. But we have to remind that wastewater treatment plant, the main target is still to produce clean effluent of the wastewater and wastewater. And of course, it was already told in the first presentation, there are different energy values in the primary sludge and secondary sludge. And there is also from the municipalities, from our households, it's coming more also bio-waste. So there is a tendency that this bio-waste or the organics coming to grease, fat that's coming from the household, it also can be digested together if there is an anaerobic plant at the wastewater treatment plant. But it has to be considered this is waste, and this is not mainly the waste the energy project, but this is the wastewater treatment process. These are quite old reference, though, but a primary sludge can be a little bit different from nowadays, because now we have a shorter retention time with primary clarifiers, but it's seen that primary sludge, secondary sludge differ quite enormously from the content of mostly proteins, and also biodegradability is different. And if we put them into the same perspective, then for modeling purposes, from stoichiometric purposes, also the stoichiometric formulas are different, and from the primary sludge, we get much more biodegradable and volatile solids, for example. So, what is the purpose of the sludge treatment itself, if we take into perspective of the wastewater treatment plant? It's two things. It's stabilization. Why do we need to stabilize the sludge? To stabilize the sludge, we need to reduce smell, but it's also improved the waterability and decrease somewhat the amount of pathogens. Second thing, sludge treatment, purpose of sludge treatment is hygienization. We don't get too much hygienization in anaerobic, but it reduces somewhat of the pathogens. So then finally, there's a decision point whether the sludge which is treated goes to agriculture or to be reused, because there is a considerable nutrient potential in the sludge, or whether we have arguments that it contains too much of heavy metals, too much drugs, hormones, or organics, then it needs to be burned. But this is the decision, and the anaerobic process has to be considered differently on these two alternatives as well. If you look on the Baltic Sea states or the EU, these are the final uses, agriculture or incineration green, and if you look on the Baltic Sea countries, we see that there is huge variability already in the Baltic Sea countries. It's leading of Germany, lots of about half of incineration, but also other countries. The main trend is to go towards the incineration. So if we look on if this way goes to the left side, so to the agriculture use, then we have a target to have the stabilization as well. If this goes to the incineration, they don't care about stabilization. Stabilization is needed, it just takes away organics, which we gain from an energetic point of view, we gain it in the incineration anyway. So then we talk about energy production, and in this process it also improves the waterability, so in drying we gain back some energy in the drying phase. Actually. So, in this case, in the anaerobic process itself is quite a simple process. It's stable because the primary sludge and secondary sludge, surface sludge coming quite stable from the wastewater treatment plant, and the only way to increase the amount of energy to the wastewater treatment plant anaerobic digester is to increase the for digestion, to increase more substrates to the process, and then it comes to the process. Then it comes to if the goal is to achieve stability, then we also have to achieve the values of stabilization. So the anaerobic stabilization as a plant is quite complex. It's lots of different equipment in the anaerobic digester. It comes with a reception station of bio-waste, for example, but thickening equipment with lots of pumps, recirculation, much more electric automation. So if we consider compared to composting, it's quite complex. Same plant from the other side, it's got heat exchanger turbines, compressors, gas treatment, gas or the ATEX and safety zones. So it's quite a complex already. And I skipped a little bit about the energy content because it was told already. So it's all about the energy which is in the wastewater. So we talk about the COD of the wastewater. So if we gain energy value about 0.5 kilowatt hours per person equivalent per day, roughly. And we have standard numbers for biogas production, which is quite big range because the COD or it depends very much on the substrate. If we have a standardized municipal sludge, not too much industrial influence, then the numbers are quite stable. But one of the best values for biogas is reduced organic solids. Reduced volatile solids is roughly 900 liters per kilogram of reduced organic solids. Although this is not really the constant either, because of the volatile solid can be also nitrogen and so on. So normal design is 20 days of toilet retention time. Volumetric loading rate is less than 2 up to 2.5 kilograms of volatile solids per cubic meter per reactor per day. But it depends on the temperature, of course, and on the reaction, and then we try to achieve the maximum organic matter removal as possible. It depends a little bit on process. And this is also old data. So this is the high rate for either digestive or the operational retention time. And how to assess really the sludge stabilization, because if you add more organics, then the final outcome of the sludge needs to be checked, whether it's stabilized or not. And there are several parameters how to check it. There is oxygen consumption, there is a volatile solids that you can assess by volatile content and by chemical methane potential. This needs to be checked in order if you start to increase more of your core digestion substrates to the process, then you need to check the biogas content as well. So, if we talk about reasons of possible instabilities, if we start to increase core digestion, for example, then one is stability of the feed. So the feed stability mainly comes from the core digestion, from the other substrate which comes to because the surface sludge and primary sludge removal from the process is quite stable. So for the wastewater treatment plant digester, we don't need to care about unless we have lots of fluctuating or new substrates. So organic overload can lead to accumulation of volatile solids or volatile fatty acids. It can lead to the drop of the pH, and also it relates to the digestate quality. The digestate quality, if it's going to be used in the greenery or in agriculture, needs to be checked if we start to overload the anaerobic digester. And this is probably the first limit comes to the digestate quality, and the second limit comes to the drop of the pH in one reactor system, for example. So hydraulic overload, this has to be also considered because some of the methogenic bacteria are quite in the consortia are very slowly growing, and if you hydraulically overload the digester, then you can get some bacteria, lack of some bacteria. Temperature changes. Of course, temperature change is bad because the bacteria consortia are stable in stable condition, and according to some references, only 1% in thermophilic biogas process, only 2 to 3 degrees in the mesophilic digester should be decreasing. So if there is a problem with heat exchangers, then the best would be to have a stable control. Ammonia inhibition. Ammonia inhibition is quite variable. It depends very much on the pH conditions in the reactor, and there are also different reports on the ammonia inhibition levels, starting from 1 to 2 grams per, or 1 to 3 grams ammonia per liter, and some report very high levels of ammonia until the inhibition is achieved. And then hydrogen sulfide inhibition, the same. And also it's dependent on the pH level, because really the inhibiting part, as in ammonia, is NH3. In this case, it's neutral molecule H2S. So this is lower in the lower pH, so the toxicity comes earlier with the lower pH of the H2S toxicity. H2S can be measured, and ammonia can be measured more in the biogas also. The antibiotics disinfectants are also an issue, but not too much in the wastewater treatment at anaerobic digesters, because the levels are very low and it doesn't reach the inhibition stage. And trace elements. This is not really usually a problem also in the anaerobic digester wastewater treatment plant, but it has to be considered. If we start to increase co-digestion, then and start to increase some very specific substrate, which gives us lots of biogas, the trace element, lack of trace element, leads to operational problems like problems of accumulation of fatty acids and so on. And how we can measure that? There are lots of different ways. There are simple ways, simple monitoring, basic monitoring ways, more advanced monitoring ways. So if we go to the feeding rate of course can be controlled, everybody controls it. And that gives us the basic data for modeling, for example, of the digester basic composition of feedstock, and also the reactor analyte of the feeding, or the feedstock analytes can be, or it's a basic information. Ammonia concentrations, gas volume and gas composition give us also lots of information, including the inhibition stages of H2S and NH3. Biogas production, biogas composition gives us information about the stages of the anaerobic digester. Temperature range, mesophilic digester is around 35 to 37 degrees, and that gives us quite stable process. However, the most important is to have a stable operation that's in the same range, not fluctuate too much. Changes are always bad. pH is normally from 7 to 8. If we have too high, then the reactor, there might be higher limitations of the ammonia inhibition, and the reactor metagenesis doesn't work well either. And if you go too low, then we probably have a overloading scenario. It can be also a scenario of microelements left. And if we talk about overloading, then there are different parameters, including VFA composition and VFA to alkalinity ratio, which also is a very easy way, simple analysis to evaluate the VFA content or overloading of the reactor. And one of the good parameters to monitor is hydrogen, because hydrogen is a very fast parameter to change. So we have two scenarios, stable and unstable, and we can measure it by different parameters like VFA and so on. And more or less, this is the end of my talk. I thank you all for.
Thank you.